Today we explore second-order derivatives and the Hessian matrix, which allow us to measure the curvature of a multidimensional function and classify its critical point. Just as a second derivative in single-variable calculus tells us whether a curve is concave upward like a smile or concave downward like a frown. Second-order partial derivatives in multivariable calculus tell us how the slopes are changing as we move across a surface. When we have a function of multiple variables, we can take partial derivatives more than once. For a function of two variables, x and y, we can take the second partial derivative with respect to x twice, the second partial derivative with respect to y twice, or mixed partial derivatives, where we differentiate first with respect to x and then with respect to y, or vice versa. By Clairaut Theorem, assuming our function is sufficiently smooth, the order of mixed partial derivatives does not matter, meaning the partial derivative with respect to x and then y is equal to the partial derivative with respect to y and then x. When we gather all these second-order partial derivatives into a square matrix, we get the Hessian matrix. For a function of n variables, the Hessian is an n by n square matrix, where the entry in the E, ith row, and jth column is the second-order partial derivative with respect to these y's, i's input variable, and the j the input variable. Let us look at a concrete mathematical example to see how a Hessian matrix is constructed. Suppose we have a function of two variables, f of x and y, defined as x cubed times y minus 5 times squared plus 2 times y cubed. First, we find the first-order partial derivatives. The partial derivative with respect to x is 3 times x squared times y minus 10 times x. The partial derivative with respect to y is x squared plus 6 times I squared. Next, we compute the second-order partial derivatives to build our 2 by 2 Hessian matrix. The top left entry is the second partial derivative with respect to x twice, which is 6 times x times y minus 10. The top right and bottom left entries are the mixed partial derivatives, which are the derivative of our x expression with respect to y evaluating to 3 times x squared. The bottom right entry is the second partial derivative with respect to y twice, which is 12 times y thus. Our Hessian matrix is a 2 by 2 grid, with the first row containing 6 times x times minus times y squared, and the second row containing 3 times x squared and 12 times y. To see why the Hessian matrix is so powerful, let us examine how it helps us classify critical points, which are locations where the gradient vector is equal to the zero vector. In single-variable calculus, we use the second derivative test to determine if a critical point is a local minimum or a local maximum. In multivariable calculus, we use the eigenvalues of the Hessian matrix or a determinant test for 2 by 2 matrices to achieve the same goal. If we evaluate the Hessian matrix at a critical point where the gradient is 0, we look at its behavior. If all the eigenvalues of the Hessian matrix are strictly positive, the matrix is positive definite, meaning the surface curves upward in all directions like a bowl, and our critical point is a local minimum. If all the eigenvalues are strictly negative, the matrix is negative definite, meaning the surface curves downward in all directions like a dome, and our critical point is a local maximum. If the eigenvalues have mixed signs, some positive and some negative, the critical point is a saddle point, meaning the surface curves up in one direction and down in another, much like a horse saddle. Let us illustrate this classification with a second concrete example. Consider the function g of x and y, defined as x cubed minus 3 times x plus y cubed minus 12 times. Why first we find the gradient by taking the first-order partial derivatives. The partial derivative with respect to x is 3 times x squared minus 3, and the partial derivative with respect to y is 3 times y squared minus 12 top. Setting both partial derivatives to 0 to find our critical points, we find that x can be 1 or -1, and y can be 2 or -2, giving us 4 distinct critical points. 1, 2, 1, -2, -1, 2, -1, and -1, -2. Next, we construct the Hessian matrix for this function. The second partial derivative with respect to x twice is 6 times x. The mixed partial derivatives are 0 because the terms do not mix x and y. The second partial derivative with respect to y twice is 6 times I. Therefore, our Hessian matrix is a diagonal 2 by 2 matrix with 6 times x in the top, left position, and 6 times y in the bottom right position, with zeros everywhere else. Because it is a diagonal matrix, its eigenvalues are simply the entries on the diagonal, which are 6 times x and 6 times y. Now we test our critical points by plugging their coordinates into our eigenvalues. For the critical point 1, 2, the eigenvalues are 6 times 1, which is 6, and 6 times 2, which is 12. Both eigenvalues are positive, which means the Hessian is positive definite, confirming that 1, 2 is a local minimum. For the critical point -1, 2, the eigenvalues are -6 and 12, which have mixed signs, making this a saddle point. For the critical point 1, -2, the eigenvalues are 6 and -12, which also have mixed signs, making it another saddle point. Finally, for the critical point -1, -2, the eigenvalues are -6 and -12. Because both eigenvalues are negative, the Hessian is negative definite, confirming that -1, -2 is a local maximum. This demonstrates how second-order derivatives and the Hessian matrix provide an indispensable toolkit for analyzing the deep geometric structure and optimization landscapes of multivariable functions.